If you step outside on a clear night and look up, the sky doesn't look empty. It looks crowded. Almost every tiny point of light you see is a star. And our sun is just one ordinary star among hundreds of billions in our galaxy alone. The galaxy itself is only one among hundreds of billions of galaxies in the observable universe. These are not poetic exaggerations. These are measurements. Now here is something remarkable. For most of human history, we did not know whether other stars had planets. It was a reasonable guess, but we had no proof. Then instruments improved. Telescopes became more precise, and missions like the Kepler Space Telescope began watching thousands of stars carefully, looking for tiny dips in brightness caused by planets passing in front of them. What we found surprised even optimistic astronomers. Planets are not rare accidents. They are common, very common. Many stars have planetary systems. Some stars have multiple planets. Some of those planets are rocky. Some are roughly Earth-sized. Some orbit in what we call the habitable zone, where temperatures might allow liquid water. None of this proves life exists elsewhere, but it does change the starting assumption. The ingredients do not appear to be unusual. Now let's slow down and think carefully. Suppose our galaxy contains roughly 100 billion stars. If even a small fraction of them have planets, that's billions of planets. If even a small fraction of those are Earth, that's millions or billions of potentially suitable worlds. Now imagine that life begins on just 1 out of 100 of those. Then imagine intelligence arises on 1 out of 100 living worlds. Then imagine technology develops on 1 out of 100 intelligent planets. At each step, you can choose pessimistic numbers. Make the probabilities small. Make them uncomfortable. Even then, the result does not easily go to zero. When you multiply small fractions by enormous cosmic numbers, you often still get large results. This is the part our intuition struggles with. We are not used to multiplying tiny probabilities by astronomical quantities. And here is the tension. If intelligent life has arisen many times in our galaxy over billions of years, and if even a few of those civilizations developed advanced technology, then in principle, some of them should have had time to expand, explore, or at least leave detectable traces. The Milky Way is about 100,000 light years across. That sounds immense, and it is. But compared to the age of the galaxy, which is over 10 billion years, even slow expansion could in theory spread across it many times. So we are left with a puzzle. The numbers suggest that life, even intelligent life, should not be unique to Earth. The timescale suggests that if technological civilizations are common and long-lived, their presence might already be visible. And yet when we look, we see no clear evidence, no obvious signals, no engineered structures, no unambiguous visitors. The universe looks fertile. The chemistry seems generous. The timescales are vast, and still the sky remains quiet. Let's imagine something simple. You walk into a vast forest that stretches for miles in every direction. The trees are tall, the soil is rich, sunlight filters through the leaves, and there is water nearby. By all appearances, this forest has everything needed for life. And as you stand still, you hear it: birds calling, insects buzzing, leaves rustling as animals move through the undergrowth. The forest feels alive not because you see every creature, but because you detect activity. Sound becomes evidence. Now imagine walking into another forest just as large, just as fertile, with the same sunlight and water. But this time there is no sound, no birds, no insects, no movement in the leaves. The air feels still in a way that is uncomfortable. You would not immediately conclude that life is impossible there. The trees are proof that something grows. But the silence would bother you. You would begin asking questions. Was there a fire? A disease? Something that prevented animals from surviving? The silence itself would become the mystery. The universe is like that second forest. We have discovered that the trees of the cosmos, stars, and planets are everywhere. The chemistry needed for life is not rare. Carbon, hydrogen, oxygen, nitrogen, these elements are abundant. Water appears to be common. Organic molecules exist in interstellar clouds. From a chemical perspective, the universe does not look sterile. It looks promising. So if the conditions seem suitable, where are the sounds? Where are the signals, the movements, the unmistakable signs that something technological is happening out there? When we point our radio telescopes at the sky, we mostly detect natural noise, radiation from stars, pulsars, galaxies. We do not detect clear, repeated, artificial patterns that scream intention. No steady cosmic beacons announcing presence. No obvious engineering projects reshaping stars. The cosmic forest appears physically rich but behaviorally quiet. One possible reaction is impatience. Perhaps we simply haven't looked long enough. After all, serious searches for extraterrestrial signals have only been happening for a few decades. On cosmic timescales, that is less than a blink. If you walked into the forest and listened for only 1 second, you might miss the bird call that comes 2 seconds later. Our search window is extremely short compared to the age of the galaxy. But even with that caution, the analogy remains unsettling. If intelligent life were extremely common and long-lasting, the galaxy might not just whisper occasionally. It might hum with activity. There might be large-scale energy use, visible astroengineering, or unmistakable patterns embedded in starlight. We do not see such things, at least not yet. This is where our expectations collide with reality. We expect that intelligence leads to expansion, communication, visible change. That expectation is based entirely on one example, us. We assume that other civilizations, if they exist, would also build, transmit, explore, and leave detectable marks. But perhaps that assumption is flawed. Perhaps intelligence does not inevitably lead to noise. Still, the comparison lingers. A fertile forest that makes no sound feels incomplete. A galaxy full of planets that shows no clear technological activity feels similar. The silence may not prove absence, but it demands explanation. One possibility is that life itself is extraordinarily rare. Not rare in the casual sense, but rare in the deep statistical sense, something that requires such a precise chain of events that it almost never happens twice. When we look at Earth, it is tempting to say that life must be easy. After all, geological evidence suggests that life appeared relatively soon after the planet cooled enough to support liquid water. In cosmic terms, it did not take billions upon billions of years. It emerged fairly quickly, but we must be careful. Quickly is based on a sample size of one planet. Imagine you flip a coin one time and it lands on heads. You cannot conclude that the coin always lands on heads. You cannot even estimate the probability accurately. With one data point, almost any explanation remains possible. Earth may represent a common outcome, or it may represent a cosmic accident so improbable that it has not occurred again within millions of light years. We also do not fully understand how life began here. We know that early Earth had water, volcanic activity, lightning, ultraviolet radiation, and a mixture of chemicals. We have demonstrated in laboratory experiments that organic molecules can form under such conditions. But forming simple organic molecules is not the same as producing a self-replicating system capable of evolution. The step from chemistry to biology, from molecules to something that can copy itself and undergo natural selection, is still not completely understood. Did life arise only once on Earth? Or did it begin many times with only one lineage surviving? If life started independently multiple times, that would suggest the transition from non-life to life is relatively easy under the right conditions. If it happened only once, it might suggest that the step is extremely unlikely. We simply do not know. There may be hidden bottlenecks. Perhaps the formation of stable, information-carrying molecules like RNA is rare. Perhaps the precise environmental stability required for complex chemistry is uncommon. Earth benefited from a large moon that stabilizes its axial tilt, plate tectonics that recycle nutrients, and a magnetic field that shields the surface from harmful radiation. Each of these factors might play a subtle but crucial role. Remove one, and perhaps life never progresses beyond simple chemistry. And even if simple life is common, complex life may not be. On Earth, for billions of years, life consisted only of single-celled organisms. Multicellular organisms appeared much later. Intelligence capable of technology appeared only very recently. Dinosaurs dominated the planet for over 160 million years without building radio telescopes or spacecraft. Intelligence, at least in the technological sense, is not the inevitable endpoint of evolution. It is one branch among many. So when we say aliens should be everywhere, we are making assumptions about how easily life forms, how often complexity evolves, and how likely intelligence becomes technologically capable. Each of those steps could be rare. If even one of them is extremely improbable, then the silence of space may not be surprising at all. It may simply reflect the difficulty of climbing from chemistry to consciousness in a universe that does not guarantee success. Now consider a more unsettling possibility. Suppose life is not especially rare. Suppose simple organisms emerge on many planets, given enough time and the right chemistry. Suppose even intelligence arises occasionally. The question then becomes not how life begins, but what happens after it becomes capable of shaping its environment. Think of development as a sequence of hurdles. First, you need the right chemical ingredients. Then you need self-replication, then stable cells, then complex cells, then multicellular organisms, then nervous systems, then self-awareness, then technology. Each step is not guaranteed. Each step may require special conditions. But imagine that many worlds manage to pass most of these hurdles. What if there is one final hurdle that is extraordinarily difficult to cross? This idea is often called the Great Filter. It suggests that somewhere along the path from lifeless matter to galaxy spanning civilization, there exists a barrier so severe that almost no species makes it past. The silence of the universe could be evidence of that barrier. The filter could be behind us. Perhaps the transition from non-living chemistry to the first cell is nearly impossible, and Earth is a rare success. In that case, we are lucky, and the quiet sky simply reflects how special that first step was. But the filter could also be ahead of us. Imagine a civilization that discovers nuclear energy. That discovery provides enormous power and enormous destructive capability. Or imagine the development of advanced artificial systems that operate beyond direct biological control. Or ecological changes driven by rapid industrial growth. A species that becomes technologically capable may also become capable of destabilizing its own environment faster than it can adapt. On Earth, we have already demonstrated the ability to alter the atmosphere, eliminate species, and build weapons that could end complex civilization in a matter of hours. We have not destroyed ourselves, but the capacity exists. That fact alone is significant. Now extend this reasoning outward. If technological intelligence tends to produce tools that outpace wisdom, then perhaps most civilizations experience a period of rapid growth followed by collapse. If that collapse happens within a few centuries or millennia of developing advanced technology, then the window during which a civilization emits detectable signals may be extremely short. In cosmic terms, 1,000 years is nothing. If civilizations flicker into existence and then disappear quickly, the chance that two of them overlap in time and are close enough to notice each other becomes very small. The galaxy may not be empty of light. It may be full of brief sparks that ignite and extinguish before their light reaches anyone else. This possibility changes the interpretation of silence. It is no longer a simple absence. It becomes statistical evidence. If long-lived expansionist civilizations were common, the galaxy might already show clear signs of their presence. The fact that it does not may suggest that longevity is rare. The disturbing part is not merely that others might have failed. It is that we may be subject to the same constraints. The Great Filter, if it exists, is not just an abstract idea about distant worlds. It is a statement about the fragility of intelligence in a universe governed by physical laws that do not guarantee survival. There is another possibility that does not require rarity or self-destruction. It requires only physics. The universe has a built-in speed limit, the speed of light. Nothing with mass can travel faster than it. This is not a technological limitation. It is woven into the structure of space-time itself. You cannot simply invent a better engine and ignore it. The faster you try to go, the more energy you need, and as you approach the speed of light, that energy requirement grows without bound. Now consider distances. Our galaxy, the Milky Way, is about 100,000 light years across. That means even if you could travel at the speed of light, which we cannot, it would take 100,000 years to cross from one side to the other. Human civilization, from the earliest cities until now, is only about 10,000 years old. Recorded radio communication is barely more than a century old, so even light itself takes longer to cross the galaxy than our entire written history. Suppose an advanced civilization exists 10,000 light years away. If they send a radio signal toward Earth 900 years ago, we would not yet have received it. If they detected our first radio broadcast from the early 20th century, they would not hear them for another 900 years. Communication across such distances is not a conversation. It is a slow exchange across millennia. Now think about travel, not just signals. Even at 10% of the speed of light, far beyond anything we can currently achieve, crossing the galaxy would take 1,000,000 years. 1,000,000 years is a long time for a biological species. It is long enough for climates to change, for evolution to reshape ecosystems, for civilizations to rise and fall many times over. Any interstellar journey would require extraordinary stability, resources, and long-term planning. And then there is the problem of energy. Accelerating a spacecraft to a significant fraction of light speed would require enormous energy. Protecting it from interstellar dust, which at those speeds would strike with tremendous force, presents additional engineering challenges. Shielding living beings from cosmic radiation over long durations adds more complexity. These are not impossible in principle, but they are not trivial obstacles. So perhaps the galaxy is not filled with visible empires because expansion is simply too difficult to sustain. Maybe civilizations develop technology, explore their own systems, perhaps send probes to nearby stars, but never spread widely enough to dominate the galaxy. The cosmic ocean may separate worlds not by emptiness, but by distance and energy cost. From our perspective, we tend to imagine expansion as natural. On Earth, species spread when resources allow it. Humans crossed oceans, built ships, developed aircraft. But those expansions occurred on scales of thousands of kilometers, not trillions. The step from crossing an ocean to crossing interstellar space is not a small increment. It is a leap of orders of magnitude. The silence of space, then, may not indicate absence of life. It may indicate isolation enforced by physical law. Civilizations could exist like islands separated by vast, dark waters, each surrounded by a bubble of detectable signals that fade into noise long before reaching another shore. The universe might not be empty. It might simply be too large and too bound by its own rules for its inhabitants to easily find one another. Even if travel is limited, you might expect civilizations to send signals. Radio waves, for example, travel at the speed of light, so communication could theoretically reach distant stars. Humans have been transmitting radio and television signals for just over a century, a tiny fraction of the age of the galaxy. Our earliest broadcasts have traveled only about 100 light years, barely scratching the surface of the Milky Way. From a cosmic perspective, that is almost nothing. The search for extraterrestrial intelligence is still in its infancy, limited both in time and scope. We have scanned portions of the sky for repeating signals, narrowband emissions, and unusual patterns. These searches are sophisticated and growing more so every year. Projects like the SETI Institute point large radio telescopes at thousands of nearby stars, listening for signals that might indicate artificial activity. Yet despite decades of effort, the results remain inconclusive. We have detected interesting anomalies, but none that can be definitively attributed to intelligent life beyond Earth. The silence persists. Part of the reason may be timing. Civilizations may exist, but their technological windows may not overlap. Consider the possibility that a civilization emits detectable radio signals for only a few centuries before transitioning to a different technology or collapsing entirely. The chance that we exist at the same time, within range to receive their signals, may be exceedingly small. Two civilizations could rise and fall in isolation, separated by thousands or millions of years, never overlapping in a way that allows communication. The universe is also vast. Radio signals spread out, weakening as they travel, eventually blending into the background noise of space. Even a powerful transmission may be undetectable at great distances. Civilizations could be broadcasting constantly, but by the time the waves reach us, they may be too faint to distinguish from natural cosmic noise. The universe is not silent because nothing exists. It may be silent because the messages are diluted, scattered, or simply too subtle for our current instruments to detect. We also make assumptions about intent and method. We imagine that other civilizations would want to announce themselves, that they would use signals similar to our own. But their motivations may differ completely. They might avoid detection deliberately, or they might rely on communication methods beyond our understanding. Perhaps they send probes or signals in forms we have not yet imagined. Our searches are constrained by what humans consider sensible, and intelligence that evolved under different conditions may think entirely differently. Time and scale compound the problem. Even if a civilization exists nearby, its signals could arrive long before or after our own. In cosmic terms, a few thousand years is practically instantaneous. In practical terms, it is nearly impossible to coordinate contact. A civilization could be listening carefully while we broadcast blindly. Or we could be listening for a century only to miss their signal that occurred millennia ago. The silence may therefore be a natural consequence of probability, timing, and physics rather than evidence of absence. The galaxy might be full of civilizations, each transient and isolated, their signals crossing paths too rarely to detect. Our expectations of communication assume simultaneity and proximity, but the cosmos operates on scales far larger than human intuition can grasp. The quiet is not necessarily empty. It may reflect the enormous challenge of connecting across space and time, the fragility of overlapping windows, and the subtlety of detection against a vast, noisy background. Another intriguing possibility is that intelligent civilizations are aware of each other, but choose not to interact. Imagine a species far more advanced than humans, capable of observing other planets without being detected, much like a wildlife biologist studies animals through hidden cameras without disturbing them. From their perspective, direct contact might be risky, unnecessary, or even ethically questionable. They could be deliberately maintaining distance, allowing younger civilizations like ours to develop naturally without interference. This idea is often referred to as the zoo hypothesis, suggesting that Earth might exist in a kind of cosmic preserve, observed but untouched. The hypothesis raises fascinating questions about the psychology of advanced civilizations. For such behavior to be possible, a civilization would need to be extremely stable over millions of years. It would have to maintain internal coordination, cultural continuity, and a consistent set of principles across generations to avoid accidental interference. This is a difficult requirement, even for small human societies, let alone an interstellar civilization spanning multiple planets or star systems. The level of patience, foresight, and stability required is extraordinary, suggesting that any civilization capable of following this principle would be fundamentally different from anything we know. This perspective also forces us to confront our own assumptions about intelligence. Humans often assume that intelligence implies curiosity, exploration, and expansion. We project our behavior onto potential extraterrestrial beings, expecting them to act as we would if given similar technology. But the universe may not operate according to human psychology. Advanced civilizations could prioritize sustainability over expansion, observation over contact, and caution over experimentation. Their goals, values, and ways of thinking might be incomprehensible to us. The zoo hypothesis is speculative, but it highlights an important limitation of human reasoning. We can only model extraterrestrial behavior based on our own experience. Our intuitions about curiosity, communication, and exploration are rooted in Earth-bound biology and social structures. Assuming that aliens would behave as humans do may be as misleading as assuming that life must exist exactly as it does on Earth. Evolution in other environments could produce minds with entirely different priorities and ways of perceiving reality. This idea also underscores the fragility of our own civilization. If advanced civilizations are deliberately avoiding contact, it suggests that interacting with younger civilizations carries potential risks. Perhaps civilizations often fail because they mismanage powerful technologies or misunderstand the consequences of their actions. Observing from a distance may be the safest way to ensure survival over cosmic timescales. The same principle may apply to us. Reaching out prematurely or misusing our emerging technologies could lead to our own extinction before we achieve long-term stability. The concept forces a broader reflection on our place in the cosmos. Even if the universe is full of intelligent life, our perception of isolation may be accurate. Silence does not necessarily imply absence. It may reflect caution, ethics, or a vastly different perspective. Advanced civilizations may exist in ways we cannot perceive, maintaining careful observation while leaving young species like ours undisturbed. The quiet of space could be a deliberate design, an outcome of intelligence operating on a scale far beyond human understanding, and a reminder of how little we know about life beyond our own world.